Let's look at problem 9. Problem 9 says find the maximum and minimum values of the objective function z equals 4x plus 5y. So I want to find the maximum value and the minimum value of that objective function. Subject to the following constraints and non-negative conditions. So here are the constraints. The non-negative conditions were that x must be greater than or equal to 0, y must be greater than or equal to 0, which puts me only in the first quadrant of my coordinate plane, doesn't it? Start by graphing the constraints and non-negative conditions. Label on the graph all the corner points of the feasible region. Construct a chart that shows the objective function's value at each of the corner points of the feasible region. Identify the maximum and minimum values and the point at which each occurs. So remember, when we graph these constraints, we are graphing linear inequalities in two variables. And what you always start graphing first is the linear equation in two variables. So you establish your line. Then you can determine which side of the line to shade to have the points that meet the inequality. So we always first graph the equation. That gives us our line. So 2x plus 3y equals 12. Let's find the intercepts. Those are typically the easiest points to find when we have the equation in standard form. So if x is 0, then y has to be, if x is x, yeah. If x is 0, can't write and talk at the same time. If x is 0, doesn't the y have to be 4, so that 3 times 4 would make 12? Or if y is 0, then x would have to be 6, so that 2 times 6 would make 12. So for this particular equation, this particular line, I have 0, 4, the point 0, 4, and the point 6, 0. So I'll draw the line, and I only have to have the line in the first quadrant because I have the non-negative conditions that x and y must both be greater than or equal to 0. And now I want the ordered pairs that will make 2x plus 3y greater than 12. The line is what makes them equal. I want those also that make it greater than. So let's put in the origin. 0 plus 0, 0 is greater than or equal to 12? No, that's false. So it's not this side, it's this side that contains the points that make that inequality true. Okay. So now, let's graph the other inequalities equality. Let's graph the other equation. And let's do the same thing. Let's get the intercepts. Well, if x is 0, then y has to be 11. And if y is 0, oh, that's not too nice. X would have to be, what, 11/3, which is 3 2/3. So if x is 0, y is 11. That's up here. It's the point 0, 11. And if x is 3 2/3, x being 3 2/3 gives me a y value of 0. So 3 2/3, let's say, is roughly there. So we've got this line. Now we want the points that make it less than 11. So let's try the origin again. 0 plus 0 is 0. 0 is less than 11 is true. So that would be the points on this side. And then the feasible region would be the region where I have both arrows, which would be this region right in here. So here's my feasible region. It's bounded by this corner point, which is the corner point 0, 11, this corner point, which is the corner point 0, 4, and this corner point. So this region right in here is my feasible region. So I need to figure out what that last corner point would be. I have the corner point 0, 4. I have the corner point 0, 11. And I'll be able to determine the objective function's value from those corner points. I just need to find that third corner point. Well, that corner point is created by the intersection of the two lines. And the intersection of the two lines is the solution to this system of two linear equations in two variables. So I need to solve this system of linear equations in two variables to determine the coordinates of that corner point. So I'm going to take this equation, multiply it by -3. That would give me negative 9x minus 3y equals -33, wouldn't it? And the reason I did that is because now I can add this new equation to this first equation, and the y's will cancel, leaving me just a linear equation in x. 2x plus -9x is -7x. 12 plus -33 is -21, gives me x is equal to 3. So the x value at this other corner point is 3. And I can take that x value, plug it into one of the equations to find y. If I plug it in here, 3 times 3 is 9. 9 plus 2 would have to make 11. So the y value there is 2. So my remaining corner point is the corner point 3, 2. And now I want to evaluate the objective function at each of those corner points. Well, if x is 0, that contributes nothing to the objective function's value, and it just becomes 4 times 5 is 20. So at the point 0, 4, the objective function's value is 20. Likewise, here at the point 0, 11, 0 for x contributes nothing. 5 times 11 would be 55. So at the point 0, 11, the objective function has a value of 55. Here, 3 times 4 is 12, plus 2 times 5 is 10. 12 and 10 is 22. At the corner point 3, 2, the objective function's value is 22. So the minimum objective function's value occurs at the point 0, 4, and the maximum objective function value occurs at the point 0, 11. And we have found all the information we were required to find. Problem done. Nice easy one like that on the test wouldn't be too bad, would it?